So far, we have looked at circuit layouts and simulation. However, you may want to design your own components, and IPKISS provides a powerful and flexible framework to do this. You can create the layout of the component as well as the interconnectivity and models to simulate it. In this tutorial, we will look at the layout by designing an MMI. To design a component in IPKISS, it is important to understand the concept of a P-cell, or a parameter cell. P-cells contain a set of parameters that are used to characterize the design, or at least a part of it. Once you've chosen a set of parameters for your P-cell, the P-cell can be instantiated. A P-cell is the blueprint for creating a component in IPKISS. It contains all the information about it in different views, layout, netlists, and circuit models. In IPKISS, P-cells are represented by a Python class. The components themselves are therefore objects created from that class. To create your own P-cells, you need to inherit from i3.pcell. In this example, we create a new class called MMI1x2, which inherits from i3.pcell. P-cells in IPKISS have what are known as views that describe different aspects of a component. These views are implemented as inner classes of a P-cell, that is, as a class that belongs to another class. For example, the layout view describes the layout of a component. A P-cell can also have other views that describe its interconnectivity or how it is simulated. To build up the layout, we will use a function called generateElements that has geometric building blocks called elements, which are shapes drawn on a particular layer. To make an MMI, we use a rectangle for the multimode section and wedges for tapers. If we look at the generateElements function to the right, we see the two elements i3.rectangle and i3.wedge. To these elements, you need to provide geometrical parameters such as the center and box size parameter of i3.rectangle. You need to also provide the layer on which the element is to be drawn to the layer parameter. We can instantiate the MMI with the usual techniques. You can instantiate its layout with .layout, and from the layout object you can obtain a lot of information. Firstly, you can visualize it using the visualize method of the layout view, which is .visualize with annotate set to true, and we can then write it to GDS. You can create a top view of the component with information on the material stacks using visualize 2D, and you can take a look at its cross-section by using the cross-section method and then visualizing it. In both cases, the 3D geometry of the component is assembled first in what is known as a virtual fabrication process defined in the PDK. You can provide the virtual fabrication process you want to use to the parameter process flow. To use your MMI in a circuit, you will need to define ports for it. This will allow you to connect your components together when you define your circuit. In the case of a 1x2 MMI, it has 3 optical ports, 1 input and 2 outputs. We define them using i3.optical port and a set of variables such as the port name, its position, and angle. You can see this to the side with the define generate ports function. We use i3.optical port and the input parameters. In addition to the other variables, each optical port requires something called a trace template. This describes the waveguide cross-section at the port. It is a type of class that describes all the information needed to create a waveguide. For example, it contains which layers the waveguide will be drawn in and the width of these layers. From this you can determine the cross-section. Extending this further, we can make the MMI parametric to the trace template. We can use the waveguide core layer to define the layers for the MMI structures. This ensures the waveguide and MMI structures are in the same layer without hard coding it, as well as generating a valid layout. Now we need to get the trace template from somewhere, and so we define it in our P-cell at the level of properties. This is where you define all the different parameters of your cell that you can vary. We provide in our properties a value to the name prefix. This will be used as a prefix to the name of each cell in your layout, which means each MMI in our circuit layout will be called MMI 1x2 1, MMI 1x2 2, and so on. Then we define the property for the trace template. We give this property the name of traceTemplate and use i3.traceTemplate property to restrict it to only inputs that are a traceTemplate. We then provide a default value to the traceTemplate. To do so, we define a method with the name defaultTraceTemplate, which means that IPKISS will take the value returned by this method and use it as the default value of traceTemplate. Following the same principle, you can make your MMI parametric to other properties too. For example, rather than hard-coding the geometrical properties of your MMI, you can define them as parameters that you can vary. You would need to define descriptive, understandable names for these parameters. In our case, we choose the names width, length, taper length, and waveguide spacing, as these describe what these parameters represent. Since they are all positive quantities, we restrict them to positive numerical values by defining them as instances of i3.positiveNumber property. We then provide default values to the default parameter of i3.positiveNumber property. We can now list these properties in our generateElements function instead of the hard-coded values. We can do the same for the elements in generatePorts. So let's go even further and make the number of inputs and outputs of our MMI parametric. By using for loops, you can loop over each input and output and create tapers and ports for them. You can see in this code example what it looks like. This is a method that you can use to make sure that the parameters of your MMI lead to a valid layout. You can make it return true except in those cases in which you know that the layout will be invalid. In those cases, it will return an exception with a customizable error message that explains the problem. This is a very useful thing to implement. In some cases, you may not want to change the parameters of your component. For example, you have a component optimized for a certain frequency. This is where a fixed cell becomes very useful. Let's say you want to easily instantiate your component with that set of parameters, and you want to avoid accidentally providing a different set of parameters. The solution is to create what is known as a fixed cell. This is a component for which the parameters are frozen and so cannot be set. To create a fixed cell, you need to add a line that says at i3.lock properties, parentheses, just before the start of your P cell. This line is known as a decorator and instructs IPKISS to lock this class to a certain set of properties. Now it's over to you. If you go to our training material in PyCharm, and for this chapter you go to the exercises.py file, you will find an incomplete P cell for a grating coupler. So here we are in the PyCharm environment, and the idea is to complete the code where you see the ellipses. If you get stuck, we do have a solutions file. There are situations in which you may need finer control in creating your layout. In this tutorial, we will go over some methods in which you can have this finer level of control. This is the case if you're working with an unusual shape. And the solution is to use i3.shape and i3.boundary. If we look at this top example, there isn't an element or a shape available out of the box in IPKISS that can follow this shape. However, we can create our own using i3.shape and pass it to i3.boundary to create our own custom element. To achieve this, we will first take a look in the documentation to see if there is any shape that is similar to the one we want. We see that there is this shape, i3.shape exponential, that contains something similar. We start by instantiating the shape i3.shape exponential with the values that we want. It is important to note that a shape in IPKISS contains a list of points which can be extracted or iterated over. Here we take only the points in the shape that are above the y-axis. This means that we obtain the points for an exponential line. We then pass these points to the points property of a new instance of i3.shape to create a shape with only these points. This is done all in one line with the following code. We call this shape top shape, as we use it for the top boundary of our exponential taper, the bottom boundary of our top trench. We create a copy of this shape and offset it by the trench width to create the top boundary of the top trench. We can add together different shapes. This creates a new shape with the list of points for each added together. By adding together the shape for the bottom boundary of the top trench to the shape for the top boundary in reverse order, we can create a total shape for the entire top trench. We can obtain the bottom shape by taking a copy of the top shape that is mirrored vertically along the y-axis, the top boundary of the top trench. We then pass these shapes to i3.boundary to create an element on a layer with these desired shapes. It is possible to create a component out of other components. The most convenient way to do so is by using i3.circuit, but there are cases in which you may want a finer level of control. In these cases, you can add references to the layout of certain components directly to other components. To do this, you need to use the method generate instances of i3.layoutView. Much the same for generate elements and generate ports, you need to overwrite the method in your layout view and have it return a list of reference elements that refer to the layout of another cell. Let's start by creating waveguides for the bus and coupling sections in the racetrack. To do this, we will use i3.waveguide. This is a P cell for a waveguide included in IPKISS that takes as input the trace template for defining a cross-section and a shape for defining the trace along which it will be drawn. i3.waveguide and its layout combines this data together to create a waveguide layout, and we can see this illustrated here, where we have our trace template, a trace, which leads to the layout. We define the shapes of our waveguides directly as a list of points. The bus waveguide shape is defined as a straight line. The start and end points are determined by the radius and half of the coupling length, indicating that this waveguide extends beyond the coupling region on both sides. The coupler length spans the length of the coupling region. We then create our waveguide using i3.waveguide, using the trace template. We use i3.placeAndRoute to define our waveguide instances and place and connect them. We can see in the code at the bottom our inst with i3.placeAndRoute. So we have an inst dictionary with our bus waveguide, coupler waveguide, and top waveguide, and our specs list, where we place each component and connect them with i3.connectBend. We finally put it all together, and we can generate our racetrack layout. Let's look at this in our PyCharm environment. In the Advanced Examples folder, we can find Explore Racetrack Resonator.py, and it has everything we've discussed in this section. Here we see the class Racetrack Resonator. We have some default lengths for the directional coupler. We have layout verification to make sure that the layout remains physical. We have an overview of our layout where we define our shapes, the bus waveguide and the coupler shape. And then we create instances of these waveguides and place them using the specs list. We generate our optical ports using i3.opticalPort. And finally, we have our main function, which creates our racetrack resonator. We define a gap, a length, a coupling length, a radius, and a vertical length. These, of course, you can change. When we run the script, we see our racetrack layout. In this tutorial, we've looked at how to create component layouts and to generate elements, which are shapes on layers. We've learned how to add ports and make the design parametric. We then looked at trace templates, which contains all the information to create a waveguide, including the layers on which it is drawn, the width of the layer, and can also include simulation data optionally. We looked at fixed cells. In some cases, you may want to keep a fixed set of parameters for a particular cell. In this case, you can lock it using a fixed cell. Finally, we looked at some advanced concepts in how to create your own custom shapes. If a certain shape doesn't exist, you can find one that's similar and make adaptations. If you'd like to learn more, please visit Lucida Academy. We have many interesting examples for you to explore with detailed documentation. And if you have any questions, please don't hesitate to contact us at support@lucidaphotonics.com.